Imagine the entire span of human existence. Every war and peace, every whispered secret and triumphant discovery, every life lived and lost. Now, compress it. Squeeze all that energy, all that fury, all that history into a single searing second. The result would be a flash of unimaginable brilliance, a cosmic event so profound it would be written into the fabric of the universe itself. This is not merely an exercise in scale. This is the genesis of the objects we are about to study. This is the birth cry of a neutron star. In the vast, dark tapestry of the cosmos, where darkness is the rule and light the exception, celestial objects typically obey a certain decorum of scale. Planets are manageable, stars are grand, and the gulfs between them are humbling in their emptiness. But neutron stars are different. They are the universe's paradoxes, its impossible diamonds forged in the most violent crucibles imaginable. They defy intuition and challenge the very limits of physics. To contemplate a neutron star is to engage with something that feels less like an object and more like a concept, a theory given terrifying, spinning form. Our journey begins with a simple, almost innocent question. What happens when a star dies? For sun-like stars, the answer is a quiet, elegant fade into a white dwarf. But for the true titans, the stars born with 8 times the mass of our sun or more, death is not an end. It is a transformation. As detailed in the chapter on massive stars, their demise in a core collapse supernova is the most energetic event since the Big Bang. And at the heart of that cataclysm, in the eye of the stellar hurricane, something miraculous is left behind. If a supernova is the cosmic equivalent of a nuclear bomb, then a neutron star is the diamond created at its ground zero. It is the remnant core of the giant, surviving the explosion not through brute strength, but through a profound metamorphosis. In less than a heartbeat, gravity performs its most extreme alchemy. It crushes the core, a sphere of iron originally the size of Earth, with such unimaginable force that electrons are slammed into protons, merging to form neutrons. The entire atomic structure of matter is annihilated, replaced by an ultra-dense city-sized sphere of almost pure nuclear material. A single sugar cube-sized fragment of this stuff would weigh as much as a mountain, over 1 billion tons. This is matter stripped to its absolute essence, a state that cannot be replicated in any laboratory on Earth. But the wonders do not end with its density. The neutron star is a bundle of cosmic superlatives. Born from the collapsing, spinning core of its progenitor, it inherits a ferocious rotation. A star that once rotated once a month may now spin hundreds of times per second, becoming a pulsar, a lighthouse of the cosmos. Its magnetic field, compressed along with everything else, becomes trillions of times stronger than Earth's, capable of atomizing a human from thousands of kilometers away and distorting the very structure of atoms themselves. These fields whip charged particles into beams of radiation that sweep across the galaxy with metronomic precision. The first time astronomers detected these pulses in 1967, they half-jokingly labeled the signal LGM-1 for little green men, so perfect and artificial did the rhythm seem. They had stumbled upon nature's most accurate clocks, ticking in the void. To study neutron stars is to probe the frontiers of physics. They are natural laboratories for states of matter we can only dream of creating, with densities that may give way to exotic soups of quarks or hyperons. Their solid crust, perhaps a kilometer thick, is a crystalline lattice of atomic nuclei, a diamond indeed, but one under such immense strain that it can fracture, creating starquakes that release more energy than our sun will emit in 100,000 years. They test the limits of Einstein's general relativity, their intense gravity bending light and slowing time in measurable, dramatic ways. This series, The Life of a Giant, is an expedition into this extreme realm. We began by setting the stage with the furious life and explosive death of massive stars. Now, we turn our gaze to one of the universe's most stunning creations. We will delve into the different species of neutron stars, the radio pulsars that blink in the dark, the magnetars whose magnetic fury unleashes titanic flares, and the strange, silent ones lurking in binary systems, slowly consuming their companions. We will explore how they shape their surroundings, powering beautiful nebulae like the Crab, and how their collisions, rippling space-time itself, create the gold in our jewelry and the uranium in our reactors. A neutron star is a monument to the forces of creation and destruction. It is a relic of a giant's life, a beacon of physical extremes, and a key to understanding the universe's most profound secrets. It is truly a diamond in the dark, not cold and inert, but pulsating with a fierce, dynamic, and terrible beauty. In its heart, it holds the answers to questions we are only just beginning to ask. Let us begin the search.
In the vast, silent theater of the cosmos, most stars are humble, steady performers, burning for trillions of years in a state of quiet equilibrium. But there exists a rare and spectacular breed, the cosmic titans, the massive stars. Theirs is not a life of gentle flickering, but a brilliant, explosive, and tragically short saga. To understand the most dramatic events in the universe, the supernovae that seed the cosmos with the elements of life and the black holes that warp the fabric of space-time, we must first bear witness to the life and death of these stellar giants. A massive star begins its journey like any other, within a colossal, cold cloud of molecular gas and dust, a nebula. A trigger, perhaps the shock wave from a distant supernova, compresses a pocket of this cloud, causing it to collapse under its own gravity. As it falls inward, it spins and flattens into a furious accretion disk, feeding the nascent protostar at its center. For a star destined for greatness, this feast is prodigious. It gathers not the meager mass of a star like our Sun, but 8, 15, even 100 times that amount. This immense weight becomes the defining characteristic of its existence, setting it on a path of ferocious speed and inevitable self-destruction. The moment nuclear fusion ignites in its core, a star is born. But for a giant, this ignition is not a gentle turning on of a switch. It is the lighting of a furnace at maximum blast. The primary fuel, as for all stars, is hydrogen, fusing into helium. However, the colossal gravitational pressure at the core of a massive star creates temperatures and densities far exceeding those in a star like the Sun. This forces the nuclear reactions to proceed at a staggering, profligate rate. A star like our Sun will burn its hydrogen fuel for about 10 billion years. A star 10 times more massive may possess 1,000 times more fuel, but it burns it with such wanton extravagance that its entire hydrogen burning phase lasts a mere 20 million years, a geological blink of an eye. It lives fast, shining with a brilliant, blue-white intensity that can outshine a million suns. This furious burning creates an outward radiation pressure that perfectly balances the immense inward pull of gravity. But this balance is a fleeting, desperate struggle. When the core's hydrogen is exhausted, it is left as a ball of inert helium. Gravity, unopposed by fusion, crushes the core further, heating it until it reaches the staggering temperature, around 100 million Kelvin, required to ignite helium fusion. The star responds by swelling enormously, but its internal drama has only just begun. This is where the life of a giant diverges fundamentally from that of a smaller star. What follows is a frantic, multi-layered descent. The exhaustion of each new fuel source, helium into carbon, carbon into oxygen, neon, magnesium, and so on, triggers another gravitational collapse, another dramatic temperature increase, and the ignition of a new, hotter fusion process. The star's interior becomes a layered onion, each shell fusing a different element, all surrounding an increasingly dense and complex core. This sequence of nuclear burning stages accelerates exponentially. Hydrogen fusion lasts for millions of years, helium fusion for perhaps 1 million, carbon burning for a mere 1,000 years. The subsequent stages are breathtakingly brief. Oxygen fusion may last only a year, and silicon fusion, which forges iron, a single, fateful day. This frantic race leads to an ultimate, insurmountable barrier, the formation of an iron core. Iron is nuclear ash. Unlike all previous elements, fusing iron does not release energy. It consumes it. For a brief moment, the iron core is supported not by fusion, but by a quantum mechanical effect called electron degeneracy pressure. The star's mighty furnace has finally run out of fuel that can sustain it. The Titan has built its own tomb at its very center. The end, when it comes, is cataclysmic. In less than a second, the iron core grows until its mass exceeds the Chandrasekhar limit for degenerate matter, around 1.4 solar masses. Gravity wins its final decisive victory. The core collapses from a sphere the size of Earth to a ball of neutrons just a few kilometers across in a fraction of a second. The implosion is so violent that it rebounds, sending a stupendous shock wave blasting outward through the infelling layers of the star. This shock wave, turbocharged by a flood of neutrinos from the newborn neutron star, rips the star apart in a titanic explosion known as a core collapse supernova. For a few weeks, this single event can outshine an entire galaxy. The violence of the explosion, a testament to the star's immense life force, forges elements heavier than iron, gold, silver, uranium, and scatters them, along with all the other elements cooked in the star's layered interior across interstellar space. This enriched gas becomes the raw material for new stars, planets, and eventually life itself. We are literally made of stardust, the ashes of these long-dead giants. What remains of the core depends on the final weight of the progenitor. It may be a rapidly spinning neutron star, a pulsar, a city-sized diamond of unimaginable density. Or, if the original star was massive enough, the collapse may continue unabated, the gravity so overwhelming that not even neutrons can withstand it. The core crushes itself into a singularity, a point of infinite density, birthing a black hole, a gravitational ghost whose pull not even light can escape. Thus, the life of a giant is a story of cosmic hubris and profound generosity. It is a life defined by mass, lived at a breakneck pace, and concluded in a blaze of self-immolation that seeds the universe with complexity. The supernova is not merely a death. It is the spectacular final act that sets the stage for everything that follows, from the formation of new solar systems to the very chemistry of life. In its death throes, the massive star ensures that its brief, brilliant life echoes throughout the cosmos for eons to come.
For millions of years, the massive star had lived a life of extravagant fury, balancing its immense gravity with the searing power of nuclear fusion. But deep in its heart, a fatal debt was being accrued. Each successive layer of nuclear ash, helium, carbon, oxygen, neon, magnesium, piled upon the core, each new fusion stage burning faster and hotter than the last. This frantic race culminated in the creation of the star's ultimate nemesis, an iron core. Iron is nuclear poison. Unlike all previous elements, fusing iron atoms does not release energy. It consumes it. For a brief, precarious moment, this growing sphere of iron, now about the size of Earth and containing more than 1.4 times the mass of our Sun, is held up by a quantum mechanical effect, electron degeneracy pressure. The electrons, packed shoulder to shoulder, simply refuse to be compressed further. But gravity is relentless. The core continues to accrete mass from the ongoing silicon fusion in a shell around it, growing heavier by the second. In its final moments, the core is a silent, inert bomb waiting for the trigger of its own weight. The end begins not with a bang, but with a silent, fundamental breaking of physics' last defense. The core's mass exceeds the Chandrasekhar limit. Electron degeneracy pressure, the very force that supports white dwarf stars, suddenly fails. It is a catastrophic and instantaneous collapse. In less than a second, the core implodes. What was a sphere the size of Earth collapses inward at a quarter the speed of light. The density soars to beyond that of an atomic nucleus. Under this unimaginable pressure, a bizarre and pivotal reversal occurs. The iron nuclei are shattered, and electrons are forced into protons, neutralizing their charge and transforming them into neutrons. This process releases a flood of ghostly particles called neutrinos. The core is no longer a plasma of atomic nuclei and electrons. It is becoming a solid ball of neutrons, a proto-neutron star. The collapse continues until the core reaches a density akin to that of a single giant atomic nucleus. At this point, a new, even more powerful force emerges: neutron degeneracy pressure. The collapse slams to a halt so abruptly that the infalling material rebounds. A mighty shockwave forms at the edge of the newborn neutron star and begins to blast outward, a spherical tsunami of energy rushing back into the still collapsing outer layers of the star. For a few critical milliseconds, the fate of the explosion hangs in the balance. The shockwave, sapped of energy as it tears apart atomic nuclei in its path, stalls. It seems the supernova may fail, the outer layers falling back to crush the neutron star into a black hole. But salvation comes from the very neutrinos created in the core's collapse. These particles, which interact only weakly with matter, are initially trapped within the incredibly dense core. But as the neutron star forms, they flood outwards in an unimaginable torrent, carrying with them 100 times the energy of the shockwave itself. This neutrino wind, a ghostly hurricane of almost massless particles, delivers a decisive blow. It re-energizes the stalled shockwave, pumping it with the energy needed to resume its catastrophic journey outward. The soundless, invisible push of trillions upon trillions of neutrinos is the final essential ingredient that unleashes the supernova. Now, the fury is unleashed. The reborn shockwave, traveling at hypersonic speeds, rips through the star's remaining structure. The outer layers, still fusing hydrogen and helium in a vain attempt to support the star, are blasted apart. The star is torn asunder from the inside out. The energy released in this single event is staggering. For a few weeks, the supernova can outshine the combined light of every other star in its host galaxy. It is the death of a single star, but the birth of a cosmic spectacle. Within this expanding fireball, temperatures and pressures reach levels not seen since the first moments after the Big Bang. The supernova becomes the universe's primary forge for the elements of life. In the frantic few seconds of the explosion, a process known as rapid neutron capture, or the R process, occurs. Atomic nuclei are bombarded by a dense sea of free neutrons, building them up into heavy elements like gold, platinum, uranium, and iodine. All the iron in your blood, the calcium in your bones, and the oxygen you breathe was forged in a long-dead star. But the gold in a wedding ring or the uranium in a power plant was likely born in the final, furious seconds of a supernova like this one. The explosion scatters these newly minted elements across interstellar space, enriching future generations of stars and planets. What remains is a rapidly expanding, brilliantly colored nebula, a supernova remnant, and at its center, the ghost of the star's core, the neutron star. If the progenitor star was exceptionally massive, even the might of neutron degeneracy pressure may fail, and the core continues its collapse into a black hole. But for many, the result is this city-sized diamond, spinning rapidly and possessing a magnetic field of unimaginable strength. The supernova is thus not an end, but a violent, creative transformation. It is the final, necessary fury that marks the death of a star and the birth of a legacy. It seeds the galaxy with the building blocks of planets and life, and it leaves behind one of the most enigmatic objects in the cosmos. The catastrophic explosion is the crucible in which the neutron star is forged, a testament to the fact that in the universe, from the most profound destruction often comes the most wondrous creation.
The life of a star is a continuous epic battle, a tug-of-war on a cosmic scale. On one side, the inward pull of gravity, the fundamental force that seeks to crush all matter into a single point. On the other, the outward push of energy generated by nuclear fusion in the star's core. For most of a star's life, this battle is a stalemate, a state of exquisite balance known as hydrostatic equilibrium. But when the nuclear fires begin to falter, gravity, patient and inexorable, prepares to win the war. The result is gravitational collapse, the universe's most powerful mechanism for crushing matter into forms beyond imagination. The seeds of collapse are sown in the very process that sustains the star, fusion. A star is a giant nuclear furnace progressively fusing lighter elements into heavier ones to maintain the pressure that holds gravity at bay. In sun-like stars, this process ends with the creation of carbon and oxygen, elements that cannot be fused to release further energy under the star's core conditions. For a massive star, the journey is far more dramatic. It builds an onion-like structure with shells fusing hydrogen, helium, carbon, neon, oxygen, and finally silicon into iron. Each stage burns faster than the last. While hydrogen fusion may last millions of years, the fusion of silicon into iron may last less than a day. Iron is the terminus of this cosmic fusion pathway. It resides at the very peak of the curve of nuclear binding energy. Fusing iron into heavier elements, unlike all previous reactions, does not release energy. It consumes it. In an instant, the star's central engine seizes. The outward pressure that has supported the star for millions of years vanishes. The stalemate is broken, and gravity, after its long wait, is unleashed.
What follows is a collapse of almost incomprehensible speed and violence. The core, now an inert ball of iron, is no longer supported by thermal pressure. It begins to fall inward under its own immense weight. The collapse is not a gentle sinking, but a catastrophic free-fall implosion. The core, which was once the size of Earth, can collapse to a sphere of just tens of kilometers in a matter of seconds. During this implosion, the core reaches densities and temperatures that transform the very nature of matter itself. The physics of this collapse hinges on a quantum mechanical principle: degeneracy pressure. This is not a force born of heat or motion, but a fundamental resistance of subatomic particles to being squeezed into the same quantum state, a consequence of the Pauli exclusion principle. Initially, it is electron degeneracy pressure that provides the last line of defense. The electrons, packed together, create a formidable outward pressure. However, there is a limit to what even quantum forces can withstand. This limit, the Chandrasekhar limit of about 1.4 solar masses, is the core's point of no return. If the iron core exceeds this mass, electron degeneracy pressure catastrophically fails. The collapse then enters its most dramatic phase. The pressure becomes so immense that it forces a fundamental change in the particles themselves. Electrons are rammed into protons in the atomic nuclei, neutralizing their charge and transforming them into neutrons. This process, known as electron capture, releases a torrent of neutrinos, elusive, nearly massless particles that rarely interact with matter. The core is now a seething soup of neutrons, and for a moment it continues to collapse unimpeded. But soon, a new and even stronger degeneracy pressure emerges: neutron degeneracy pressure. As the core is compressed to densities comparable to that of an atomic nucleus, a state often described as a single, giant atomic nucleus, the neutrons, like the electrons before them, resist being packed any closer together. If the remaining mass of the collapsing core is not too great, this neutron degeneracy pressure will bring the implosion to a sudden, shuddering halt. The collapse rebounds, sending a tremendous shockwave blasting back outward through the infouling material, leading to a supernova explosion. This, however, is not the end of the cosmic crush's power. The final outcome is dictated by a simple, brutal calculation: the total mass of the remnant core, the neutron star equivalent of the Chandrasekhar limit. If the collapsing core remnant is between roughly 1.4 and 2.5 solar masses, the neutron degeneracy pressure wins. The core stabilizes as a neutron star, an object so dense that a single teaspoon of its material would weigh billions of tons. But if the remnant core exceeds this upper limit, the cosmic crush achieves its ultimate victory. Not even the fierce resistance of neutron degeneracy can withstand the star's immense gravitational weight. The collapse continues unabated. The neutrons themselves are crushed out of existence. The matter is compressed into a point of infinite density, a singularity. A black hole is born, and an event horizon, a point of no return for light and information, forms around it. Gravity has finally and completely won. Gravitational collapse is thus the universe's ultimate alchemist and architect of extremes. It is the engine that forges the densest matter in the cosmos, powers the most brilliant explosions, and creates the most profound mysteries. It demonstrates that when the nuclear fires die, the true awesome power of gravity is revealed, capable of crushing a star into a diamond or erasing it from the visible universe entirely.
The supernova is the universe's most spectacular funeral pyre, a blaze of light so intense it can outshine a galaxy. But like a phoenix, something rises from the ashes. The outer layers of the star are blasted into space, seeding the cosmos with the elements for new worlds and new life. Yet the heart of the giant remains. It did not vaporize. It underwent a metamorphosis so extreme that it ceased to be ordinary matter. It is the ultimate survivor, a neutron star. This is not a corpse cold and inert. It is a zombie, a terrifyingly active, dynamic and powerful remnant of a dead star. Animated by the ferocious energies of its own collapse, the transformation begins in the supernova's inner sanctum. In the fraction of a second when the core collapses, what was once a sphere of iron the size of Earth is crushed by gravity into an object no larger than a city, perhaps only 20 kilometers across. In this process, matter is stripped to its absolute essentials. The immense pressure forces electrons and protons to merge, canceling their charges to become neutrons. The result is a core composed almost entirely of these subatomic particles, packed together with virtually no empty space. A single cubic centimeter of this neutron-rich material, no larger than a sugar cube, would weigh over 1 billion tons on Earth. This is a state of matter that cannot be created or studied in any laboratory on our planet. It exists only in the aftermath of stellar apocalypse. But to call this object simply a ball of neutrons is to underestimate its bizarre complexity. Theorists propose that a neutron star is structured in layers, like a cosmic onion, each more exotic than the last. The outermost layer, a crust, perhaps 1 kilometer thick, is a crystalline lattice of atomic nuclei, predominantly iron and nickel, so compressed that it forms the hardest, strongest material in the universe. Yet, swimming through this rigid lattice is a sea of free electrons, giving the crust incredible electrical conductivity. Beneath this solid shell, the density increases to the point where atomic nuclei are squeezed together so tightly that they lose their individual identities, merging into a continuous, superfluid sea of neutrons. This neutron superfluid can flow without any friction, a property that may explain the star's occasional sudden increases in spin known as glitches. Deeper still, at the very core, physics as we know it breaks down. The pressure may be so immense that even the neutrons themselves break apart into a soup of their constituent quarks. This could create a quark-gluon plasma, a state of matter that hasn't existed freely since the first microseconds after the Big Bang. Alternatively, the core might solidify into a hyperdense crystal, a true cosmic diamond at the heart of the zombie star. The true nature of the core remains one of the greatest mysteries in astrophysics. This bizarre internal structure is matched by an equally dramatic external existence. The neutron star inherits the angular momentum of its progenitor's collapsed core. Just as an ice skater spins faster by pulling in their arms, the star's drastic shrinkage causes it to rotate at incredible speeds. A star that once rotated once per month may now spin hundreds of times per second. This rapid rotation, coupled with an immensely powerful magnetic field, trillions of times stronger than Earth's, creates a dynamo of cosmic proportions. The star becomes a pulsar, the universe's most precise lighthouse. The intense magnetic field channels charged particles into beams of radiation that shoot out from the magnetic poles. If these poles are misaligned with the star's rotation axis, the beams sweep across space like the beam of a lighthouse. From a distance, if Earth lies in the path of this sweeping beam, we observe a pulse of radiation with every rotation, a blink that can be as regular as the most accurate atomic clock. The discovery of these pulses in 1967 was so perfectly timed that astronomers briefly entertained the possibility they were signals from an extraterrestrial civilization. They had, in fact, discovered the zombie heart of a dead star, ticking with metronomic precision. Yet, not all neutron stars are peaceful pulsars. Some are born with even more extreme magnetic fields, becoming magnetars. These are the true monsters of the undead stellar world. Their magnetic fields are 1,000 times stronger still, so powerful that they can twist the star's solid crust, causing catastrophic starquakes that release colossal bursts of gamma rays and X-rays. In a matter of seconds, a magnetar can release more energy than our sun will emit in 100,000 years. This is not the quiet fading of a corpse, but the violent thrashing of a cosmic zombie, capable of affecting the entire galaxy from its grave. The neutron star, therefore, is a paradox. It is the remnant of a cataclysmic death, yet it teems with violent, energetic life. It is incredibly dense, yet capable of starquakes and superfluid flows. It is a relic of the past, but its rapid spin and precise pulses make it a tool for probing the future of physics. It is a zombie, a dead star that refuses to be still, forever animated by the unimaginable forces of its own creation.
Density is one of those ideas that seems simple until you begin to follow it to its extremes. At its core, it is nothing more than the amount of matter squeezed into a certain space. We see it in everyday life. Wood floats on water because it is less dense. A rock sinks because it is heavier for its size. Oil layers above water because it is lighter. These are intuitive comparisons that make sense to us because we can hold them, weigh them, and see them interact. But density becomes almost impossible to grasp when we look beyond the ordinary, when we look at stars, collapsed cores, and remnants of explosions, where matter is crushed into forms that no earthly material can approach. To even begin imagining this, we often turn to the diamond, a symbol of solidity and compactness, as a stepping stone into the unimaginable. Diamonds are already extraordinary in our human scale of experience. They are forged from carbon atoms, bound in a crystalline lattice, each atom locked in place by strong covalent bonds that leave almost no wasted space. This tightly knit structure is what gives the diamond its famed hardness and its apparent perfection. When you hold a diamond, there is a sense that you're touching something unusually solid, something that feels more compact than ordinary stone or metal. Its density is about 3.5 grams per cubic centimeter, meaning that a cube the size of a sugar cube weighs a little more than 3 grams. That is heavier than water, heavier than aluminum, heavier than most familiar materials. And in everyday terms, we are tempted to call it dense. Yet this so-called pinnacle of compression is laughably light when compared to what the universe does to matter in the aftermath of stellar death. The first step beyond diamond comes with white dwarfs, the remnants of medium-sized stars, like our sun. When such a star exhausts its fuel, it sheds its outer layers and leaves behind a glowing ember, a core made mostly of carbon and oxygen. The atoms inside this corpse are so crushed together that the electrons are stripped of their freedom, pressed into a degenerate state where quantum mechanics itself provides the pressure to hold the star up. Imagine the entire mass of the sun, more than 2,000 trillion kilograms, compressed into a sphere the size of Earth. The density works out to around 1,000,000 grams per cubic centimeter. Compare that to diamond's 3.5, and suddenly the jewel seems like froth. A single teaspoon of white dwarf matter would weigh as much as an elephant. The analogy to diamond works here only as an entry point, a way to anchor the imagination before stretching it almost beyond breaking. And yet even this is not the ultimate. When a star much larger than the sun collapses after a supernova, the compression goes further still, past the resistance of electrons themselves. Protons and electrons are crushed together into neutrons, creating what we call a neutron star. These objects are perhaps the most extreme form of matter we can even attempt to describe without invoking black holes. A neutron star can be more massive than our sun, yet packed into a ball no larger than a city. Its density is on the order of 100 trillion grams per cubic centimeter. To make sense of this, imagine a sugar cube of neutron star material. It would weigh about 1 billion tons. If such a fragment could be placed on Earth, it would sink through the crust and continue until it carved its way to the planet's core. The diamond, once our symbol of the ultimate in density, looks not merely fragile in comparison, but almost meaningless. Still, we continue to reach for diamonds in our analogies because they are the densest objects we can personally encounter. They are familiar, tangible, and already imbued with a sense of rarity and strength. When someone tells you that a white dwarf is like a diamond the size of Earth, you can begin to sense the scale. You can picture the glittering hardness of the jewel, and then try, however imperfectly, to magnify it until it becomes a world. The analogy fails in strict accuracy, but it succeeds in something more important. It opens a door. It invites awe. It gives us a foothold on the cliff face of cosmic extremes. The deeper truth is that the universe operates on scales that no analogy can ever fully bridge. Density is not merely a number in this context. It becomes a revelation about how matter behaves when pushed beyond the limits of chemistry, beyond the rules that shape the substances we hold in our hands. What looks solid to us is mostly empty space. Squeeze out that space, and you move from diamond to white dwarf, from white dwarf to neutron star, and finally to black holes, where density is no longer even a definable quantity. Along the way, our language cracks under the weight of the concepts, and all we can do is compare, multiply, and hope to glimpse the enormity of it all. When we say unimaginable density, we mean precisely that. It resists full comprehension, but beginning with something familiar, like a diamond, we can at least take the first step. We can hold in our palm a tiny stone and let it hint at something far larger. The crushing weight of stellar remnants, the compression of matter into forms we cannot replicate, the ultimate recycling of the cosmos as stars live and die. Diamonds are beautiful, but in the grand scheme, they are fragile echoes of something infinitely denser and infinitely stranger. They are reminders that even the hardest thing we know is only the shadow of what is possible when the universe bends matter to its will.
Gravity is the quiet sculptor of the universe. It is at once the weakest of the fundamental forces and the one most responsible for shaping the large-scale cosmos. Gravity built the planets, gathers stars into galaxies, and ensures that moons trace their orbits faithfully around their hosts. We feel it in the most ordinary way every time we drop a pen, climb a staircase, or watch a stone fall to the ground. Yet while gravity seems tame to us on Earth, just strong enough to hold us to the surface and give our bodies weight, it becomes something altogether different under extreme conditions. To explore this transformation, one must travel in thought to the densest objects in the universe, where gravity ceases to be gentle and instead becomes overwhelming, almost incomprehensible. The phrase, "a mountain on a pinhead," captures this difference perfectly. It suggests the idea of something unimaginably massive resting on something impossibly small. This is not a poetic exaggeration, but a surprisingly accurate metaphor for the gravitational conditions that exist on stellar remnants, like white dwarfs and neutron stars. On such bodies, surface gravity reaches levels so extreme that our familiar intuitions collapse along with the atoms themselves. Consider Earth first as a reference point. The surface gravity here is about 9.8 meters per second squared, a number so ordinary that it frames the entire human experience of weight. A person who weighs 70 kilograms on Earth would weigh only about 12 kilograms on the Moon, where the surface gravity is about 1/6 as strong. On Jupiter, with its immense bulk, that same person would weigh nearly 170 kilograms. These numbers are impressive in relative terms, but still manageable by human imagination. They are changes in scale, not in kind. Now imagine compressing Earth itself down to the size of a marble. Its mass would not change, but its density would. Suddenly, standing on its surface would subject you to a gravitational pull so fierce you would be crushed instantly. This thought experiment is only a prelude to the true extremes that nature itself has already created. When a star like our Sun dies and becomes a white dwarf, it is still roughly as massive as the Sun, but it has collapsed to a sphere only about the size of Earth. The result is a surface gravity hundreds of thousands of times stronger than what we know. If you were to stand impossibly on a white dwarf, you would be pinned to the surface with a force that no material could withstand. A person who weighs 70 kilograms on Earth would effectively weigh tens of thousands of tons. It is here that the metaphor of a mountain on a pinhead begins to make sense. The weight of Everest compressed into the area beneath your foot, but white dwarfs are only the first step. Neutron stars, the collapsed remnants of much larger stars, go further. They pack more than the sun's mass into a sphere scarcely 20 kilometers across, smaller than a city. The density here is so extreme that protons and electrons have fused into neutrons, creating matter that resembles a giant atomic nucleus. On the surface of such a star, gravity is about 100 billion times stronger than on Earth. If you dropped a pebble from just 1 meter above, it would strike the surface at nearly half the speed of light. A human body, or any normal matter, could not exist in such conditions. The tidal forces alone would tear atoms apart before they even touch down. What does it mean to say that gravity is 100 billion times stronger? Numbers of this size quickly lose meaning. Analogies help. Imagine balancing Mount Everest on the tip of a sewing needle without the needle snapping. That is the kind of compression and force we are talking about. Or picture holding in your hand a pinhead that weighs more than every building in a major city combined. The metaphors are clumsy, but they try to capture the sheer absurdity of the numbers. This unimaginable surface gravity has strange and beautiful consequences. For one thing, it bends light itself. On Earth, gravity is too weak to noticeably curve light, but on a neutron star, the gravitational field is so intense that photons follow curved paths. If you stood on a neutron star, ignoring the impossibility, you would be able to see not just the hemisphere around you, but almost the entire surface at once, because light from the far side would be bent around to your eyes. Gravity has literally changed the rules of vision. Another effect is time itself. According to Einstein's general relativity, the stronger the gravity, the slower time passes relative to a weaker gravitational field. Clocks on the surface of Earth tick ever so slightly slower than clocks on satellites orbiting above us, a difference so small it matters only for GPS calculations. But on a neutron star, the effect becomes profound. A second on its surface could stretch into hours when compared to time far away in empty space. In these crushing gravitational fields, even the flow of time is distorted. Surface gravity also dictates how matter behaves when falling in. On Earth, a meteor burns up because of atmospheric friction, but on neutron stars there is often no thick atmosphere, just a thin veil of particles. Matter does not simply fall. It slams down with cataclysmic violence. As it hits the surface at near-light speed, its kinetic energy is converted into radiation, producing bursts of X-rays detectable across the galaxy. In this way, the surface gravity of neutron stars transforms them into cosmic beacons, and yet even neutron stars are not the final word. Black holes represent gravity pushed beyond all measure, where even the concept of surface gravity becomes strange. There is no surface at all, just an event horizon, a boundary beyond which escape is impossible. To speak of surface gravity here is to speak of escape velocity equal to the speed of light. A mountain on a pinhead no longer suffices as a metaphor. The image collapses, much as the star itself collapses into singularity. What is perhaps most astonishing is that these objects are not distant abstractions. White dwarfs and neutron stars populate our galaxy in the thousands and tens of thousands. Black holes lurk unseen, revealed only by their gravitational influence. The cosmos is filled with these monuments to density and gravity, scattered like reminders that the universe is not tame, but wild, filled with extremes beyond human experience. To contemplate surface gravity at these levels is to recognize both the fragility of our home planet and the enormity of what lies beyond. Earth's gravity is gentle enough to allow mountains to rise, oceans to flow, and creatures to walk upright. On a neutron star, nothing stands, nothing flows, nothing survives in recognizable form. Gravity there is not the quiet sculptor, but the overwhelming master, pressing a mountain into a pinhead and time itself into new shapes. The metaphor of a mountain balanced on a pinhead is more than a vivid phrase. It is a doorway into the recognition of how profoundly alien the universe can be. It is a reminder that what we take for granted, the steady pull of Earth's gravity, the weight of our own bodies, the comfort of knowing that stones fall and rivers run downward, is only a local rule, a mild expression of a force that elsewhere becomes nearly infinite in its power. To explore surface gravity in its extremes is to be humbled, to be awed, and to glimpse, however briefly, the vast strangeness of the cosmos.
When we imagine the surface of a star, most of us think of raging fire, turbulent oceans of plasma and incandescent storms. That image is not wrong for an active star like the Sun, but it fails completely when we look at the remains of stars that have burned out their nuclear fuel and collapsed into compact remnants. In these dead stars, matter is compressed to densities so staggering that it ceases to behave as it does on Earth. Instead of fiery chaos, what we find is something paradoxical: order. At the surface of certain stellar remnants, white dwarfs in particular, atoms arrange themselves into vast crystalline patterns. The star, once a furnace, becomes a kind of cosmic diamond, a sphere with a crust of unimaginable hardness. This is the perfect crust, and its existence challenges everything we think we know about matter. To understand why such a crust forms, we must begin with the nature of the white dwarf. A white dwarf is the cooling remnant of a medium-sized star. After the star exhausts its fuel and sheds its outer layers, what remains is a dense core, no longer able to fuse elements but still radiating heat. The mass of the white dwarf is comparable to that of the Sun, but its volume is roughly that of Earth, meaning its density is hundreds of thousands of times greater than anything we encounter here. At such densities, atoms are stripped of their usual structure. Electrons are forced into a degenerate state, creating a sea of negatively charged particles that provides pressure against collapse. What remains behind in the lattice are bare atomic nuclei, carbon and oxygen mostly, floating in this electron ocean. This unusual environment gives rise to equally unusual physics. At sufficiently low temperatures, the positively charged nuclei no longer jostle freely. Instead, they begin to lock into place, forming an ordered, repeating lattice. This is crystallization on a cosmic scale, and it happens not at the scale of gemstones or minerals, but across the entire surface of a star. Imagine a diamond not the size of a jewel, not the size of a mountain, but the size of a planet. That is the reality. The crust of a white dwarf is an immense crystalline structure, rigid and enduring. On Earth, crystals form because atoms seek the lowest energy arrangement, one in which their bonds are satisfied. Salt crystals, snowflakes, quartz, all are expressions of order emerging naturally from chaos. In a white dwarf, however, the pressures are so immense that bonds as we know them no longer exist. What drives the crystallization here is the interplay between the repulsion of nuclei and the sea of electrons around them. The electrons provide a background that allows nuclei to settle into stable positions, arranging themselves in vast, repeating patterns. The result is sometimes called a Coulomb crystal, named after the electrostatic force that governs the behavior of charges. This crust is not thin, like the brittle shell of an egg. It is deep and formidable, extending for hundreds of kilometers in some cases, depending on the star's composition and cooling rate. The deeper one goes into the crust, the more tightly the nuclei are packed, until eventually the crystalline order gives way to a dense fluid interior. The star, then, is not just a diamond-like object. It is layered, with a crystalline shell surrounding a more fluid, degenerate heart. The physical strength of this crust is another of its astonishing qualities. Laboratory tests of crystalline matter on Earth are limited by size and by the weakness of chemical bonds, compared to the pressures inside stars. But astrophysicists who model the crust of white dwarfs and neutron stars suggest that these cosmic crystals are billions of times stronger than steel. They could support mountains only a few centimeters tall, any higher, and the crushing gravity would flatten them instantly. But within those constraints, the crust is as rigid and unyielding as any structure the universe has produced. It is quite literally the strongest known material in existence. The presence of such a crystalline crust has profound consequences for the behavior of white dwarfs. As the star cools, the crystallization process releases latent heat, much like water freezing into ice. This slows the cooling of the star, prolonging its glow. Astronomers who measure the light curves of distant white dwarfs can detect this cooling delay, providing observational proof that crystallization is indeed occurring. In other words, the twinkle of an ancient star is altered because deep within it, a cosmic diamond is solidifying. There is also a kind of poetry in this process. A star that once burned brightly, fusing hydrogen into helium and radiating energy into the cosmos, ends its life not in chaos but in a quiet settling into order. The wildness of nuclear fire gives way to the serenity of crystalline structure. Matter that once roared with fusion now whispers in stillness, locked into a pattern of mathematical perfection. The perfect crust is, in a sense, the final signature of the star's existence, a reminder that even in death, order can emerge from collapse. The idea of stars as diamonds is more than a metaphor. In 2004, astronomers discovered a white dwarf in the constellation Centaurus that has crystallized to such an extent it is effectively a diamond 10 billion trillion carats in size. It has been nicknamed Lucy, after the Beatles' song Lucy in the Sky with Diamonds. Such discoveries bring a human dimension to the cosmic story. We find in the heavens not just fire and gas, but something familiar, something that sparkles in the same way a jewel does in our hands. And yet, the scale of the perfect crust defies our attempts at intimacy. A diamond ring may be precious, but a crystallized star is beyond all value, beyond possession. It is matter arranged into its most perfect form, a lattice that stretches for thousands of kilometers, cold and hard and silent in the void. No hand can touch it, no tool can cut it, no human craft can imitate it. It exists only in the aftermath of stellar death, as a monument to the strange alchemy of density and pressure. The strange, crystalline structure of a white dwarf's surface is a reminder that the universe is filled not only with fire and chaos, but also with hidden geometries, with perfection born of extremity. We are left with a vision both humbling and beautiful, that stars, in their twilight, do not simply fade away. They crystallize, forming a perfect crust, a cosmic jewel that drifts through eternity, silent testimony to the order hidden within the universe's most violent transformations. To journey inward through the layers of a neutron star is to move through a landscape that no human eye will ever see, a realm more alien than science fiction. At the outermost layers, we find the strange crystalline crust, where nuclei arrange themselves into immense Coulomb lattices, rigid and unimaginably strong. But as we descend, the pressure builds and the familiar structure of matter begins to collapse. Nuclei are squeezed together so tightly that they can no longer hold their identity. Electrons merge with protons, leaving behind a world dominated by neutrons. Here begins the quantum sea, the neutron superfluid, a state of matter unlike anything on Earth, governed not by classical physics but by the eerie, counterintuitive rules of quantum mechanics. The word superfluid itself suggests something magical, an exotic fluid that flows without resistance, able to creep through cracks, climb walls, and move indefinitely without losing energy. On Earth, the phenomenon has been observed in liquid helium cooled to just a fraction of a degree above absolute zero. In this state, helium atoms condense into a single quantum wave, behaving collectively as if they are one. Pour a bit of superfluid helium into a dish, and it will not stay still. It will climb the sides and spill over, seeking to spread endlessly because viscosity, the usual stickiness of liquids, has vanished. That behavior alone is astonishing. But in the heart of a neutron star, the effect is amplified on a cosmic scale. Instead of helium atoms, we are dealing with neutrons, trillions upon trillions packed together under pressure so enormous that the normal repulsion between them is overcome. They too fall into a quantum state, forming a sea of superfluid neutrons. In this neutron superfluid, the rules of everyday liquids are irrelevant. It does not slosh or churn the way water does, because it has no internal friction. Energy injected into it persists, flowing in great ghostly currents that never fade. To imagine what this means, picture a whirlpool that never slows down, not after seconds, not after centuries, not even after the lifetime of the universe. Once the superfluid is set into motion, it simply keeps going. The neutron star's interior, then, is not a dead, solid core, but a restless quantum ocean, alive with movements that never tire. One of the strangest aspects of this sea is that, although it is fluid, it can only rotate in discrete ways. In classical fluids, rotation can be smooth. Pour milk into coffee and watch the spirals curl any way they please. In a superfluid, however, quantum mechanics demands that rotation is carried by quantized vortices, thin, thread-like whirlpools, each carrying a fixed amount of angular momentum. In the heart of a neutron star, these vortices thread through the superfluid interior, like an invisible forest of spinning filaments. Their arrangement determines how the entire star spins, and their collective behavior influences the star's observed rotation. This connection becomes visible in pulsars, neutron stars that emit regular beams of radiation as they rotate. Astronomers have measured their spins with incredible precision, and yet, from time to time, pulsars display sudden jumps in speed, tiny glitches that defy the otherwise perfect regularity of their timing. The leading explanation is that these glitches are caused by the neutron superfluid within. As the star gradually loses energy, its crust slows down, but the superfluid interior, free from friction, resists slowing. The vortices pinned to the crust suddenly unpin, transferring angular momentum in a catastrophic rush. The star's spin abruptly changes, like a clock whose gears suddenly catch and tick forward a fraction of a second faster. These glitches, observed from thousands of light years away, are echoes of the hidden quantum sea deep inside. The sheer scale of this superfluid is staggering. On Earth, producing superfluid helium requires cooling matter to near absolute zero, stripping away thermal energy until quantum effects dominate. In a neutron star, temperatures remain at millions of degrees, hot enough to vaporize any ordinary substance. Yet the density is so high, and the quantum interaction so intense, that superfluidity arises anyway. This inversion of intuition, that superfluidity thrives not in cold, delicate lab experiments but in one of the most violent, crushing environments in the universe, reminds us that nature is not bound by our expectations. This neutron superfluid is also thought to coexist with superconductivity. In the depths of the star, protons, though far fewer in number, form pairs much like electrons in superconductors on Earth. These pairs move without resistance, allowing currents to flow unimpeded. The result is a hybrid interior, a neutron superfluid threaded with superconducting protons and suffused with magnetic fields of unimaginable strength. This marriage of superfluidity and superconductivity creates a realm where quantum effects shape matter on macroscopic, even planetary scales. The quantum sea also raises profound questions about the nature of matter itself. Neutrons are not fundamental particles but composites, built of quarks bound by the strong force. At even greater depths inside neutron stars, where the pressure continues to climb, neutrons may themselves dissolve into quark matter, creating another, even stranger sea. The neutron superfluid may thus be only a prelude to deeper layers of exotic physics, hidden from our view, but hinted at by theory. The star, then, is not a frozen corpse, but a laboratory of quantum extremes, where matter reveals new forms that cannot exist anywhere else. For all its strangeness, the neutron superfluid is not entirely alien to us. It shares a kinship with the superfluid helium studied in laboratories, with superconductors that power our magnets and technologies, with the delicate quantum states of matter now explored in ultra-cold experiments. The difference is one of scale. In the lab, we control drops and samples. In the cosmos, the quantum sea spans tens of kilometers, containing a mass greater than the sun. It is the same physics, but magnified until it becomes something almost mythic, a vast ocean of quantum matter adrift among the stars. To journey inward, then, is to leave behind the familiar and surrender to the strange. The neutron superfluid is a reminder that the universe is not built only of rocks and gases and plasma, but also of states of matter that defy common sense. It is a sea where friction vanishes, where rotation becomes quantized, where sudden glitches ripple outward to betray the hidden currents within. It is a sea that flows without end, timeless and inexhaustible, born from collapse and yet eternal in its motions. The quantum sea is the heart of the neutron star, the place where the ordinary laws of matter collapse and the quantum world rises to cosmic scale. To think of it is to realize how narrow our daily experience is, and how vast the possibilities of matter truly are. The neutron superfluid whispers of a universe far stranger than the one we see. The universe where even in death, stars do not simply fade. They transform into oceans of quantum perfection, forever flowing in the dark.